Search for Linux interview questions and you will find 100 lists to memorize. Here is what is wrong with all of them. No two Linux interviews ask the same questions. They do cover the same 10 topics. Learn all 10 and the exact wording stops mattering. 10 topics: storage, networking, processes, memory, permissions, and the ones people forget until they are sitting in the interview. What the machine even is, and how you look something up when you do not know the answer. Almost anything they ask lands inside one of these. Every one of the 10 gets answered 4 times over. First, the answer that gets you through the question. Then a better one, the kind that shows you have actually done this. Then we read the screen together, line by line, because that is where the next question comes from. And last, something to go and try for yourself. One warning before we start. Some of what follows breaks a machine on purpose. A bad mount file stops it booting. One rebind puts a private service on the network. Use something you can throw away, not something anybody depends on. Question 1, and it sounds like a warm-up. You have just logged into a machine you have never seen before. What do you check first? 2 commands. Uname -r for the kernel, then cat the OS release file for the distribution. Say both plainly and take the tick, because everything you claim after this depends on getting it right. The command most people reach for, lsb release-a, is not installed on server or container images. The OS release file always is, and the ID like line in it tells you whether apt or DNF is coming. One command, hostname ctl, gives you all of that, plus the field nobody thinks to ask about. Chassis. Is this real hardware, a virtual machine, or a container? And if you want only that answer, systemd detect virt. On bare metal, it prints none and exits non-zero, so a script can branch on it without parsing a thing. This box is not hardware, and that changes how you read everything else on it. Start at chassis, hardware, virtual machine or container, and the line below names which hypervisor. 2 identifiers align apart, doing opposite jobs. One is written when the system is installed and survives every reboot. The other is new on each one, and it is the boundary journal CTL-B counts back from. Architecture. Get this wrong and you install the wrong package or pull the wrong container image. 12-year-old firmware on a brand new system. It belongs to the hypervisor, not to you. And it is the first link in the boot chain. 4 questions in a command you had already run. That is the whole method. Do not memorize answers. Read the output until it stops surprising you. 3 things to try. Run systemd detect virt on your laptop in a virtual machine and inside a container and watch it give 3 different answers. Run hostname ctl inside a container and see which fields vanish. Then compare the kernel version on a host and in a container running on it. Identical. That one fact is what a container is. The answer. Uname -r first, then cat the OS release file. The trap. LSB release is missing from server images. Ahead of it, hostname ctl gives you all of it in one command, and systemd detect virt answers whether this is even a real machine. How do you check this system's IP address? It sounds like the easiest question on the list. It stops being easy the moment the machine has more than one address, which in production it always does. IPA, every address on every interface. Notice the name before anything else. It is not ETH0 anymore. It is built from the slot the card sits in, so it survives a reboot instead of racing for a number. And if you were about to say ifconfig, it went away years ago, and it could never show you more than one address on an interface anyway. There is a shorter way to read it, IP-BR-CA, and a better way to answer the question. IP root get, and then a destination. It sends no packet. It asks the kernel which root and which source address it would pick to reach that destination. That is the only honest answer to what is my IP on a machine with more than one. Add a second address, ask again, and the source that leaves has not moved. 2 different states on one line. The first is what you configured. The second is whether anything is actually plugged in. The hardware address, and this one belongs to a well-known emulator. The hardware is virtual. Question 1 told you that a different way. Dynamic means this address came from DHCP, not from a file. You can search the disk all day and never find where it was set. The address is rented, not owned, under 24 hours left on the lease, and it can come back different. A link local address, one the kernel gives every interface, not routable, and not this machine on the internet. 5 questions in a single interface. 2 of them say the same uncomfortable thing. The address on this box is not yours to keep. Take the link down and watch both states change from the console, never over SSH. Ask for a route to your own subnet and then to the internet, and notice the source can differ between them. Then, run it inside a container and on the host underneath. Different namespace, different answer, one kernel. The answer is IPA. The trap is that if config is gone and was always blind to a second address, ahead of it, IP route get, which asks the kernel which address would actually leave per destination. The disk is full. What do? Everyone knows the first command. The interview starts at the point where its answer stops explaining anything. df-h, which file system and how full? Read the mounted on column before you read a single number because most of these lines are not disks and the one that matters is rarely at the top. And there is a second question. The same command answers with one flag changed. df-I counts inodes rather than blocks, and a file system can run out of those with gigabytes still free, then refuse to create one more file, while the used percentage never moves. Now the case where df and du disagree. A file is not gone when its name is. Removing it takes away the name. The blocks stay until the last program holding it open lets go. So df counts space handed out, and du counts what still has a name. Kill the reader, and 500 megabytes comes back. These 3 do not add up, and that is correct. 400 megabytes are reserved on the root file system, and only root may spend them. The name says logical volume, which means it can be grown while it is still mounted. That is the fix almost nobody reaches for. Not a disk. On current Ubuntu, the temporary directory lives in memory, so filling it costs you RAM, and everything in it is gone at reboot. A small separate file system that fills up with old kernels. It is the most common disk full ticket there is. 4 tiny 1 megabyte mounts, 1 per service. Systemd puts each unit's credentials in its own file system so the secrets never touch the disk. 5 questions in the command everyone already knows. 10 file systems on this machine, and only 2 of them are a disk. Sweep every process for a deleted file somebody is still holding open. Exhaust inodes instead of blocks on a file system you can afford to fill, and watch gigabytes free turn into no room for one more file. And learn the flag that keeps the directory walk on one file system, because without it, the number it gives you is meaningless. The answer? df-h for the file system, then du for the files. The trap? Run df-I as well, because running out of inodes looks like plenty of space. Ahead of it. When the 2 disagree, a file has lost its name, but not its last reader. What file systems are mounted on this machine? The junior answer lists them. The answer that gets you hired notices which ones are real and checks the file that decides what comes back after a reboot. Find mount. 26 mounts on an idle server, and 2 of them came from a disk. df counted 10 in the previous question because it leaves out the kernel's own file systems. Find mount leaves out nothing, so nearly all of what you are looking at is the kernel describing itself to you. Add --real, and you are down to the 2 that came from a disk. The old command, mount, still works, but it gives you one flat list and no way to ask that. Find mount --fstab reads the file that decides what comes back, and find mount --. Verify is the check to run before you find out the hard way. It reads the file instead of mounting anything, so it is safe on a machine that is up. Read the warnings, not the summary. 1 hex digit wrong in an identifier and the summary still says 0 errors, while the line above it is the one that ends in an emergency shell. This reads the file systems as well as the devices, so one command answers both what is attached and how full it is. 1 megabyte and no file system at all. It holds the bootloader, and it exists only because this machine boots the old way. This string is why the mount file does not name the device directly. Device names are handed out in probe order and can change. This cannot. 3 lines for one file system. A partition, a volume group on top of it, and the logical volume above that is what is actually mounted and what can be grown. 4 questions in one listing of the disks. That stack in the middle is why the root file system is not simply called by its partition name. Put no fail on a non-critical entry, break its device, and reboot something you can throw away. Without it, the boot waits 90 seconds for a device that is never coming, then drops you at an emergency shell. With it, the machine comes up missing one file system and nothing else. The answer is find mount. The trap is that mount still works and tells you far less. Ahead of it, find mount -- real for only the file systems that came from a disk, and find mount -- verify before you reboot. A service will not start. Walk me through it. 2 commands answer this properly, and almost every candidate stops after the first one. Look at what happened here. systemctl start reported success. 9 milliseconds later, the service was dead. With the default type, systemd calls a unit started the moment it forks, so start is not a check. Systemctl status is, and even status only prints the tail. The 2 lines that name the missing binary come from journal ctl-u and nowhere else. Systemctl cat, and this is the one that separates people. 2 files. The first came with the package. The second is a drop-in somebody added with systemctl edit, and status never mentions it at all. Look at what they do together. The packaged line ends in a variable, and the drop-in sets that variable. The command that actually runs appears in neither file on its own. 3 separate facts on one line. The file that defines the service, whether it starts at boot, and what the packager intended. None of them means it is running. This one is socket activated. Systemd holds the port itself and starts the service on the first connection, so a stop service still answers. The configuration is tested before the daemon starts. Notice what a passing test looks like here. The failed unit 2 screens ago said something different on this same line, and that is the commonest reason a service will not start. Every service gets its own control group. That is the same mechanism a container uses to hold its processes, and it has been on this screen the whole time. 4 questions in a header most people read 2 lines of. The last one is a container question, sitting here all along. Give a unit a start command that does not exist and watch it try 5 times in 10 seconds, give up, and refuse to try again until you clear the counter. Edit a packaged unit properly with an override rather than by touching the vendor file. And edit a unit without reloading to see the most common wasted hour in systemd. The answer? systemctl status first, then journal ctl-u. The trap. The old service wrapper still works for status and knows nothing else. Ahead of it, systemctl cat, which shows you the unit with its overrides, and status never will. How do you see what is listening on this machine? Everyone knows the command. Most people run it in a way that hides the one column they came for and then decide it is broken. ss-tulpn. Everything this machine is listening on. 5 flags, and you should be able to say what each one is for. TCP, UDP, listening, process, numeric. Now look at the process column on the right. It is empty, and nothing is broken. You are not root, and the kernel will not tell you who owns a socket that is not yours. One word, sudo, and the column fills in. Without it, you learn that something is listening. With it, you learn what. And look at the one for SSH. 2 owners, the daemon and systemd itself as process 1. Systemd opened that socket at boot and handed it over, which is the same socket activation the previous question found in its header. On a socket in listen, these 2 are not bytes. One is how many connections are waiting to be accepted. The other is how many may wait before the kernel starts refusing. On the lines above, they are bytes queued, and the state column is what tells them apart. Port 68 is the DHCP client. This is the process holding the lease that question 2 watched counting down. Listening on every address this machine has. Compare it with the line below, bound to loopback, which nothing outside the box can reach. That distinction is most of network security. The systemd resolved stub. Every name lookup on this machine goes here first, which is why the resolver file points at a loopback address instead of a real name server. The same service again on IP version 6 on its own line. A firewall rule that only covers the first one leaves the second door open. 5 questions in 8 lines of sockets, and the last one is the mistake. A firewall that only knows about version 4 has not closed the port. Start a listener as your own user and run it again without root. Your own process appears while every other line stays blank, which tells you root was never the requirement. Ownership was. Then bind something to loopback. Try to reach it from another machine and rebind it to every address. That one change is the whole difference between a service and an exposure. The answer is SS-TULPN. The trap. Without sudo, the process column is empty and nothing is wrong. Ahead of it, run the same command under sudo, then read the bind address, because loopback and every address are different worlds. A process is eating the CPU. How do you find it, and how do you stop it safely? 2 traps in one question. The number everybody quotes is not a percentage, and the column everybody reads is not measuring now. 1 process and 2 correct numbers. This one slept for 2 minutes and then started spinning. 49 seconds of work in 3 minutes of life is 27%, and that is exactly what PS reports, because it divides processor time by how long the process has existed. Top compares 2 samples a second apart and reports 100. Both are right. Only one of them answers the question you were asked. Find it with PS sorted by processor use, then stop it. Plain kill sends term, which asks. Watch the second one. It trapped that signal, ignored it, and carried on at 99%. Nothing told you, only kill-9 sends. Kill, the signal a process never sees and cannot refuse. Try plain kill first, and if it is a service, system CTL stop the unit, because system D will simply put it back. 1 minute, 5 and 15. Not a percentage of anything. It counts tasks that want to run, plus tasks stuck waiting on storage, so on 2 cores, 2 is full. 4 states, counted, running, sleeping, stopped, and zombie, which is already finished and waiting for its parent, which is why killing one does nothing. The state missing here is the one that matters. 8 numbers, and 2 of them decide whether the problem is even yours. One is the processor idle because storage is slow, the other is the hypervisor giving your cycles to somebody else. What the process asked for, what it actually holds in memory, and how much of that is shared. Only one of the 3 is really its own. 2 seconds of processor time across an hour and a half of uptime. This column is a total. The one beside it is supposed to be a rate, and the first screen of this question watched them come apart. No memory at all on any of these. They are kernel threads with nothing in user space, and you never try to kill one. 6 questions before you even reach a process that is doing anything. 3 of them say the same thing. The processor is often not the part that is busy. Pin a core with a shell loop and watch the load average take minutes to climb and minutes to fall. Renice it and watch nothing change, because on an idle machine, there is nothing to yield to. Start a second loop and the niced one collapses. That is what nice actually decides. The answer. PS sorted by processor use to find it, then top to see what it is doing now. The trap. PS averages the whole life of the process. Ahead of it, plain kill first, then kill-9, and remember a service comes back unless you stop the unit. Is this machine out of memory? The command is one word. Reading it correctly is where most of the question is won and lost. Free-H. 2 gigabytes were written and read back first, so the cache you are looking at is a file that just went in. Now watch what happens when it is dropped. The free column jumps by nearly 3 gigabytes. Available moves by 100 megabytes across the same 2 readings, which is exactly why it is the only one of the 2 that answers the question. Read available, not free. When it really does run out, ask the kernel what it decided. Journal CTL-K searched for the out-of-memory killer. Watch the cache column across these 2 readings. 244 megabytes before, 63 after. The kernel reclaimed every page it could and then killed something anyway. Nobody has to guess whether it was memory. The kernel logs the decision, the process that triggered it, and the score it used to pick a victim. 337 megabytes free, nearly 3 gigabytes available. The difference is the cache you just watched fill, and every byte of it comes back the moment something asks. 2.7 gigabytes of page cache, and you know exactly what it is. The file read a moment ago. It looks like memory in use, and it is not, because every page already has a copy on disk, 0. And this machine does have swap. This line counts only pages written out and since read back, still held in both places. The demonstration a moment ago put 6 megabytes out and never read them back, which is why this stayed at 0 anyway. 46 megabytes of heap and stack with no file behind them. Nothing on disk holds a copy, so the only way the kernel reclaims these is to write them to swap first. 1/4 of a gigabyte hot, 2.5 cold, and all of it discardable because the disk still holds the original. That is the whole reason cache counts is available. 5 questions in 12 lines of kernel counters. 2.5 gigabytes here can be taken back without asking anyone. 46 megabytes cannot be taken back at all without swap. Read the score the kernel uses to choose a victim, then set the adjustment on one process and watch it move. That number is on the end of the log line, and it is how you decide who dies before the kernel decides for you. Then run the same allocation under a memory limit and meet the out-of-memory kill people actually get. The 1 containers hit. The answer is free-H, the trap. Read available, not free because cache is handed back on demand. Ahead of it, journal CTL-K for the kernel's own report and the pressure file under proc for how bad it is right now. A user gets permission denied on a file they can obviously read. Diagnose it. Almost every candidate goes straight to the file. The file is almost never the problem. Watch this being built. chmod 644 on the file so everybody can read it. Then chmod 640 on one directory 2 levels above it, and the read is refused. Nothing in the file's own permissions explains that, which is exactly why the file is the wrong place to look. Every directory along the path has to permit traversal first, and on a directory, the execute bit does not mean run. It means you may pass through. So walk the whole path with name I-L as the user who failed, never as yourself. The file itself is readable by anybody. The refusal happens 2 levels above it, at a directory with no execute bit, and name I stops on exactly the component that said no. Now look at the error message from a moment ago. It named the file. The file is fine. Every permission denied you will ever read names the thing you asked for, never the thing that refused it. The user ID grants almost nothing. The groups grant everything. One of these is administrator, and another is root by a longer road on most machines. One name points at this inode. A second name for the same file carries the same owner and the same mode, so you cannot give one name different permissions from another. The same permission written twice, octal and symbolic. And look at the group, not root. Anyone in it reads every password hash on this machine without ever becoming root. 4 timestamps, and the third is the one people miss. One is when the contents changed, one is when the metadata changed, and a permission change moves it without touching a single byte. 4 questions in one identity and one file. Neither command knows about the other, and the denial you are chasing lives in the gap between them. Set an access control list that denies one user. Then look at the file the normal way. The mode still reads the same, and the only tell is a plus sign on the end of it. Point a service at a file in your home directory and watch it fail, because your home almost certainly will not let the service account through. And create a file, change your mask, create another, and find out where the default mode came from. The answer: ID for the identity, then stat on the file. The trap: it is almost never the file, and every directory in the path needs execute. Ahead of it, name I-L walks the whole path. Run as the user who actually failed. How do you look something up when you do not know the answer? The oldest question on the list and the only one whose honest answer has genuinely changed. Man-K and search the manual for anything you like. Except there is no manual. This is a stock server install, and server and container images strip the pages out by default, so the answer everybody gives is missing from exactly the machines where the question gets asked. You cannot install them with no network, and you cannot install them on a full disk either. So the answer has to be something the machine is incapable of losing. Ask type what you are actually holding, then ask the thing itself. 3 different kinds of thing, and each one is looked up a different way. A binary answers --help. A shell built-in answers help, which is why the manual page for change directory has never worked for anybody. An alias answers neither. And no manual will ever mention it, because it only exists in your shell. And if you had not read that help text to the end, you would not know the search path variable existed. Not decoration. This tool prints its help to the error stream, not the normal one, so piping it into a search finds nothing at all until you fold one into the other. Tools disagree about which stream to use, and none of them warn you. 2 usage lines, and the second one takes a filter. There is a whole query language here that most people never find, documented further down this same output. The first flag in the list is the one that printed the list. Every binary carries its own documentation inside it, which is precisely why an image builder cannot strip it out. You used this one in question 6. It stops the tool turning port 22 into a name, which matters most on the day the name is wrong. A flag almost nobody has used, sitting 3 lines from ones you use every week. Reading the whole list is how you find the one that solves the problem you have today. And this is the one that came back empty without root. Nothing on this line says so, and that is the honest limit of a help text. It tells you what a flag does, not what it needs. 6 questions in a help text you never read. 2 of them you had already used without reading them, and 1 needed root without ever saying so. Take a command you use every day and read its help from the first line to the last. Run the type command on everything in your muscle memory and find out how much of it is not a program at all. Then solve the harder half, the one where you do not know the name, because searching is the part help cannot do for you. The answer used to be man. The trap is that server images ship without it, and -- help is compiled into the binary where nothing can strip it. Ahead of it, type tells you what kind of thing you are holding because that decides how you ask. That is all 10. You will not get these 10 questions word for word. You will get these 10 topics. So run the commands yourself. Read every field of what comes back and break each one on purpose on a machine you can throw away. Know all 10, and the exact question stops mattering.